Welcome to the first video on torsion in indeterminate structures. In this video we'll go through the basics of indeterminate structures in torsion, how they relate to indeterminate structures we've seen elsewhere in axially loaded structures and in beams, and we'll talk about our two equilibrium and deflection equations that we need to maintain in order to be able to solve this problem and determine what our two reactions are. If we're seeking to solve for the reactions of an indeterminate structure that is a torsion bar, what we're going to find is that torsion shares some characteristics with axial loading. It of course shares characteristics with moment. It is moment, but about a different axis than the other moments we've thought in the past. And of course it's going to share attributes with shear because, as we've discussed earlier, the units, the stress that it's going to be experiencing is going to be shear. So it's going to have a combination of all the things that we've talked about in the past going on. So if we're looking at a problem such as this, where we have two fixed ends that are going to prevent us from allowing this bar to twist, one at A and one at B, and we have some torsion applied at C, well then, as we talked about last week with solving our indeterminate structures using deflection, consistent deflection, and that, we're going to want to use our boundary condition that the rotation at point C is equal to the rotation at point C. What a silly, fun tautology that is. But the rotation at point C, or the twist at point C, if we go from A to C, and we're at 125 millimeters, if we go from there to there, is equal to the rotation from C to B, 0, if we want to start over right there. Now that's not really necessary for us to think about with something this simple. With something this simple, we can just say that the rotation for this portion has to be equal to the rotation for this portion. There's no reason for us to sort of plot that, but we can if we want. So, and that's going to be in addition to the equation for the summation of moment about the x-axis. Right, if this is the x-axis along here, this moment is going about there. I drew it very poorly. I guess I should have left a little space there so that we could see which way is which. This is meant to be positive torsion. So summation of moment about the x-axis, of course, has to be 0 for our equilibrium equation, and so that's going to be positive 120 kilonewton millimeters, or Newton meters, but the rest of it is in millimeters, so plus our moment reaction at A. I'm just going to call that A, and B, because we're unworried about the forces in the y direction, the forces in the x direction, and I think that's probably more clear than anything else. So now we've got two equations, two unknowns. Let's start setting up our equations for the twist, the angle of twist. We have this formula from earlier, the length times our shear stress is equal to our radius times the angle of twist, which of course we can go ahead and rearrange this into, use a different color, that our angle of twist is going to be equal to the length times the shear strain divided by the radius. And if we want to, we don't have to think about this as a function of the location as we go out from the center, because I mean this right here, the shear strain, is going to be a function of our radius. So obviously this will also be L, the maximum shear strain for our outer radius. That's probably the easiest way to deal with this. So we've got two values for this. We have the one for AC, and we have the one for CB. They're both going to have the same value for this, so they are going to have the same maximum strain, because they've also got the same length, right? Both of them are 125 millimeters. However, they don't have the same cross-section. We've got a solid bar from A to C, and then we have from C to B a hollow bar. So now that we've got this as our plan, we're going to have to rearrange this further to get our shear strain.